So combinations, again, the important thing with combinations is the order does not matter. So there's a number of times that we want to count things where it doesn't matter the order. We want a group of 5, maybe for your group quiz tomorrow. I got to pick the groups, and I picked the groups of Cole, Reese, and Kyle. And Kyle says, I don't like this group. Can you pick another one? And say, okay, how about if I do Kyle, Reese, and Cole? Oh, okay, that's fine. Well, that's the same group. I just said it in a different order. You would get mad if I said, we're going to make new groups, and I just change the order in the groups, and you'd say that's not really new groups. So when the order doesn't matter, it becomes a combination question. In a combination, there's less combinations than permutations because we divide out that order. Now, using our formula we were talking about with cards before, if I have 52 cards and I choose all 52 of them, how many ways could that be done? One way. There's your deck of cards. If you have 52 cards and you choose one of them, how many ways could that be done? 52 ways. Now, we use, and on our formula sheet, we have the Ncr formula, and it's equal to n factorial over n minus r factorial times r factorial. You will see in some textbooks, this shouldn't have a line, so you can scribble that out or erase it or white out it. You will see in some textbooks the combination formula written that way, as n over r. So if you take a university class someday that has combinations, you might see that form of the formula. We've already seen in other examples too that choosing a group of 6 from a group of 10 is exactly the same as choosing a group of 4 from a group of 10. So we can do that in other examples. Sometimes there's questions like this. 7 choose 3 is equal to 7 choose B, and B doesn't equal 3. What's B equal to? B would have to equal 4, because choosing a group of 3 from 7 is the same as choosing a group of 4 from 7. In the game of poker, you get 5 cards, and it doesn't matter. When you get those 5 cards, you can rearrange them, so the order doesn't matter. So how many poker cards are possible? You choose 5 cards from 52. I might have to check that. I think that is the amount. If you do 52, choose 5 in your calculator, see if that number is right. And so if I take, for those of you that play poker, if I take these cards, I mix them up, and I take this card, 3 of clubs, 6 of hearts, there we go, 6 of diamonds, 2 of clubs, and the 2 of diamonds, we get a poker hand. And you may never see this exact same poker hand ever again in your life, because the chances of me getting these 5 cards are like 1 in 2.6 million. Is this amazing? Yeah. Well, the hand is actually not too bad. It's got 2 pairs, but part of what makes poker intriguing is that there's so many different combinations of cards that you could get. So your chances of getting the same hand again are quite unlikely. Here we've got another question where we're counting 2 different things. We want a committee of 2 boys and 3 girls. So we have 2 main decisions that need to be made. We need to choose our boys and we need to choose our girls. 15 boys, we need to choose 2 of them. 18 girls, we need to choose 3 of them. Since we have 2 decisions to make, we'll multiply those together. And again, you have the choose button on your calculator. You can find it by pushing math and then going over to probability. And I think it's the third one down. Can you see in this question that you would have 3 decisions to make? You want to split your class up into 3 different groups, Group A, Group B, and Group C. So you have 3 main decisions to make. Once you make those groups, can you see that the order doesn't matter in those groups? So if you've got 3 main decisions to make, decision 1 is who's going to be in Group A. Decision 2, who's going to be in Group B, and decision 3, who's going to be in Group C. How many choices do we have for Group A? Choose 8. Because anybody could be in Group A. And 20 choose 8 makes all the possible groups of 8 that you could have without the order mattering. Now, how many choices do we have for Group B? There's only 12 people left, right? And we need to choose 7 of them. No, choose 5 of them. 12, choose 5. And how many choices do we have for Group C? 7 choose 7. And 7 choose 7 is equal to 1. Now, it should make sense that once you've chosen everybody for Group A and everybody for Group B, and you haven't been chosen yet, and you go, what group am I in? Well, you're going to be in Group C, because you're the only group that's left, right? And so there's only, whoever is left is those last 7 people, they're going to be in Group C. And if you multiply all of these together, you are going to get the total amount of ways that you could split your class into 3 different groups. So again, I'll let you do the calculator part to figure that out. The last thing we're going to look at is we're going to look at poker hands. And so here, the first question is, how many poker hands have no clubs? Well, if I took my deck of cards and I wanted to guarantee that I dealt you 5 cards that had no clubs, what I could do is I could go through the deck and just start taking out the clubs. Because if I took out all 13 clubs, then when I dealt the cards, does it make sense that I could guarantee that you won't get any clubs? So now, I take the now 39 cards and I deal 5 cards. See if I can do it without any clubs. Yes. Yes. Ooh. Oh, no longer exciting. All right. So there's 5 cards, and for sure I would get no clubs because I've taken the 13 cards out. So now when counting those, how many poker hands have no clubs? Well, I just have to choose 5 from 39. And this is actually a very pretty number. Doesn't that look pretty? There are 575,757 poker hands without any clubs. Now, what I'm going to do for this last question, how many poker hands have at least 1 club, is I'm going to be a salesman. I'm going to try and sell you 3 different strategies. I'm going to try and sell you that all 3 strategies work. I'm going to tell you right now that it may be that all 3 strategies are wrong and do not work. It may be that all 3 strategies are right and they all work. It may be that 1 is right and 2 are wrong, or 2 are right and 1 is wrong. You have to be the responsible consumer and don't fall into the salesman's traps of which ones are right and which ones are wrong. Okay, so here we go. Poker hands with at least one club. I'm the salesman. Here's pitch number one. This is the right method. What you have to do to guarantee that you have at least one club. I've already got the 13 clubs here separated. If I take these 13 cards and choose one of them, happens to be Jack of clubs, and put that into my hand, so 13, choose one, that will make sure that I have one club in there. Then if I take the rest of my deck, put the other 12 clubs back in, shuffle it up, choose 4 other cards, 1, 2, 3, 4, and look at, oh, I happen to get another club, but that's okay, because I wanted to have at least one club. But I had the club from before to guarantee that. So now I have 51 cards left, and I choose 4 of them, and then I've guaranteed that I have at least one club in there. Multiply those out, get my answer, and that's method number 1 for solving this question. Method number 2, also a correct way to do this, is, well, I counted earlier today how many poker hands were possible, 52 choose 5. And in part A, we counted how many ways of having no clubs. No clubs was 39 choose 5. So if I use the not strategy, where I count all of them and subtract the bad ones, what I would be left with would be poker hands that have at least one club. Strategy number 3. Strategy number 3, I am going to count at least one club means either getting 1 club, or getting 2 clubs, or getting 3 clubs, or getting 4 clubs, or getting 5 clubs. That's what at least 1 club means. So I'm going to use cases. I'm going to count everything separately. Case 1, how many have 1 club? Well, I have my 13 clubs separated there. If I choose 1 club, and from the other 39 cards, choose 4 others, that will be exactly 1 club in that. In case 2, I'm going to choose 2 clubs. Okay, so of my 13 cards, I choose 2 clubs, and from my other 39, I choose 3 other clubs, 3 other cards. Ooh. Case 3 is getting exactly 3 clubs. Well, from my 13 cards, I choose 3, and from my other 39 cards, I choose 2 other ones. Case 4 is 4 clubs. How do you count 4 clubs? 13 choose 4, and 39 choose 1. And finally, case 5, choose 5 clubs, which is just 13 choose 5. If I figure out each of those cases, and because it's a cases question, add them up, my total will be the amount of having at least 1 club. So those are the 3 strategies. Of course, as a salesman, I'm telling you all 3 work perfectly. Do you agree or do you disagree? 3,278,000. 248,700. That is the best looking 4 I've ever seen. Perfect. There we go. That's a beautiful 4. And what did you say the second one was?
All I did to figure out it was different is I subtracted that number by the answer on my calculator that it would have been the second one, and it was negative 600.
Okay.
So there was a difference of 600.
So here we'll figure out what the second one is. Here 52 choose 5 202, 2023, 203. Okay, so they're different. So that means either both of those are wrong, or one is wrong and one is right, but it can't be that both of them are right. So now you know that the salesman has at least told you one lie. Yes. First one is wrong, you think why? Good observation. If the total number of poker hands is 52 choose 5, which is 2.6 million, something must be wrong in one if you have more poker hands have at least one club than possible poker hands in total, because that is over 3 million. If you figured out and added up all the cases in part 3, you would also get 202, 2023, 203. So now are the second two both right or the second two both wrong? Definitely right, because the teacher wouldn't spend this much time on a question teaching 3 wrong strategies. Okay, so they have to be right. Good logic, yes. Both strategy 2 and strategy 3 are correct. And probably as a nicer strategy, strategy 2 is nicer because it's shorter. If you take all of them and subtract the ones that have no clubs, you would be left with hands that have at least one club. But it could also be done by counting individual cases. So what goes wrong in question number 1? It seemed so good. It felt like that was, I was almost going to buy that strategy for myself after I explained it. I thought I did such a good job. No. Okay. Well, what goes wrong in number 1 is, let's think about it. 13 choose 1 chooses a club. Say I choose the 6 of clubs. Then I put the other cards back in the deck, mix them up, and choose 4 more. So for choosing the 4 more, I could have chosen the ace of hearts, the 7 of clubs, the king of spades, and the 4 of diamonds. Now, another possibility, when choosing the 13 choose 1, I could have chosen my 7 of clubs first, and then when I mixed the other cards back in, I could have chosen my ace of hearts, my 6 of clubs, my king of spades, and my 4 of diamonds. And in this method, that would have counted those 2 as different. But can you see that those are exactly the same hands? How do we recognize when we do this? Because when we think about doing this strategy, it seemed to be good. Okay? Well, the reason we ran into a problem is whenever we break up things separately, we have to make sure that there is no overlap in these 2 things. And there is overlap in this question. I could choose my 6 of clubs first, or I could choose a 6 of clubs later, and it will count it as different. Whereas in the cases, can you see here that there is no overlap? I'm choosing clubs on their own, other cards after. I'm not able to choose the same card in different places. So when you do have that overlap, you start to count things more than once. In fact, we counted, if you look at the right answer at 2 million something and the wrong answer at 3.2 million, we just overcounted a little bit, like by 1.2 million. You know, no problem. I hate that when that happens. You're going through a cashier, they accidentally give you 1.2 million more in change than they're supposed to. So it's just a little mistake that we made. But the number that came out was huge. So we have to be careful when we're counting things that we don't overlap. Now on your notes, does it end on the back side of a page, or do you have a blank page at the back? It ends on the back side? Okay, then turn to page, you have a blank page in your notebook on page 734, we are going to do a few more examples and count some poker hands. What we're going to try to do is make sure that we don't have any overlap, like we talked about with this last example, and we're going to find out why some poker hands are better than other poker hands, just by the amount of combinations that there are. We're going to start off, let's just start off with a single pair. So in poker, to get a single pair means you have two cards that are the same, but the other three cards are all different. How do we count this? How many poker hands have one pair? Well, the way that we're going to look at this is we are going to count the pair at one time and all three single cards at another time, because we count groups of cards that are the same size at the same time. And you'll see what I mean by that after we've done a couple of examples. So how do we count how many different ways we could get a pair of cards? Well, first of all, how many different numbers are possible in a deck? You could have ace, 2, 3, 4. How many different kinds are there? There's 13. So in counting our pair, we have to choose which of the 13 cards are going to be our pairs. Maybe we have a pair of fives, maybe a pair of 7, maybe a pair of kings. So the 13 choose one decides on the kind. And in our example, it's fives. Now, how many fives are in a deck? 4. And to get a pair, how many of those fives do we need? We need just 2 of them. So we take our 13 choose 1 and we multiply it by 4 choose 2. This together counts all the different pairs that are possible. After counting all the different pairs that are possible, we need 3 more single cards. How many cards are left? We can't choose fives again. There's 12 different kinds left. And of the 12 kinds of numbers that are left, we need to choose 3 of them. And we need to choose those 3 at the same time so that we don't get order. Because an ace of hearts, 7 of hearts, king of hearts is not different than choosing 7 of hearts, king of hearts, ace of hearts. So we choose all 3 of them at the same time. If we chose aces in those 3, how many aces are there? There's 4 aces. And we need to choose which one of the 4 we're going to keep. There's 4 sevens, and we need to choose which one we're going to keep. And there's 4 kings, and we need to choose which one we want to keep. And all of this together gives us 3 single cards. And all the possibilities of 3 single cards. And if we multiply all of this together, we have all the ways of getting one pair and 3 different cards. So again, what we did as a strategy is we looked at the sizes of our cards. We have single cards and a pair, and we count those things at the same time. So we counted our pair first, and then we counted our single card second. So if we do a second example here where we count something quite similar, which is 2 pairs, our example of that could be 2 sixes, 2 sevens, and a 9. So now we're going to count those together because our pairs are the same size, and the 9 separate. Well, when picking my pairs, I have 13 cards to choose from, and I have to choose 2 numbers. And I choose those 2 numbers at the same times because 6s and 7s isn't going to be different than 7s and 6s. Now, how many 6s are in the deck? There's 4, and I need to choose which 2 6s I'm going to keep. How many 7s are in the deck? There's 4, and I need to choose which two 7s I'm going to keep. All of this together counts our 2 pairs. And then we still need a single card. We have 11 numbers left. We need to choose which one we're going to choose for a single card. If we choose 9s, how many 9s are there? There's 4 9s. And we need to choose which one we're going to pick. Now that single card, if you think my 6s and 7s have already been used up, I have to take those 8 cards out of the deck, I would have 44 cards left. I could just do 44 choose 1. That would be the same as 11 choose 1 times 4 choose 1 if I wanted. But this keeps the pattern idea the same. If you figure out what this number is, it's substantially less than the first one because it is less likely to get 2 pairs than it is to get 1 pair. Yes?
What you just said regarding, we could just put it 44 choose 1?
Yep, for this part here is equal to,
R equal, we just multiply the,
well, when, like 11 choose 1 is just 11, and 4 choose 1 is just 4, and 11 times 4 is 44.
So with the 2 pairs, could we just go 4 times 13, 4 times 13, and then be that number choose 2?
No, and with the 2 pairs, you have to choose which 2 numbers you're going to pick first, and then 4 choose 2, 4 choose 2 after that. So we'll do one more. What would you like to figure out? Full house, 3 of a kind, 4 of a kind. Royal flush is easy because there's just 4 of them. Hearts, spades, diamonds, and clubs, and you're done. Straights are a little bit tricky. So you won't get asked a straight, but they're not super hard to do, but let's do a full house. A full house in poker is when you get 3 of one kind and 2 of another kind. It's actually pretty easy to count because this is what you have to separate. There's one group of 3 and one group of 4. I'll finish it up. If you want to go, I'll put it on YouTube. So there are 13 cards. Choose one for your 3 of a kind. There's 4 3s. You choose 3 of them. This will be your 3 of a kind. 12 cards left. Choose one for your 2 of a kind or your pair. And then 4 choose 2.